Welcome everyone, and thank you for joining us today. I'm excited to kick off this presentation on the evolution of good stove designs. Today, we'll explore how our designs have developed over time, starting from our first version, with 22 innovative designs, to our latest advancements. We'll also introduce you to Dr. Sai Bhaskar Reddy, our CEO, and share some key insights and contact information. So let's get started and see how our journey has progressed. Let's start by thinking about the basic elements involved in cooking with traditional methods. We have bricks and stones, which are often used to build the structure of the stove. These materials are durable and can withstand high temperatures. Then, we have fuel, which is essential for producing the heat needed for cooking. Notice that fuel is listed twice here, emphasizing its importance. Without fuel, the entire process stops. Now, an important aspect to consider is the air from all sides. Good airflow is crucial because it ensures the fire burns efficiently and consistently. Proper ventilation helps control the temperature and makes the stove safer to use. Finally, we see the mention of a 3-stone stove. This traditional design uses 3 stones to support the cooking pot, allowing for good airflow around the fire and making it easier to manage the heat. All of these points connect to our overall theme of understanding simple yet effective cooking techniques, especially in resource-limited settings. They highlight how traditional methods rely on fundamental materials and principles to create a functional and sustainable cooking environment. Let's take a look at some common types of stoves used in various settings. First, we have the metal stove, which is quite popular because of its durability and ease of use. Then, there's the cement stove, which tends to be more sturdy and can withstand high temperatures, making it a good choice in many environments. Moving on, we see the side air design, which is important because it influences how the fuel burns and how efficiently heat is transferred. Next, we have the annular stove, which is typically open. This design allows for good airflow and can be quite effective for certain cooking needs. Finally, the type of fuel used is a crucial factor, as it impacts the stove's performance, cost, and environmental impact. Understanding these different stove types helps us choose the right option for specific situations, aligning with our overall goal of improving efficiency and sustainability in cooking methods. All right, let's take a closer look at Slide 4, which focuses on clay and bricks. As you can see, clay has been a fundamental material for building for thousands of years, mainly because it's readily available and easy to shape. When we talk about bricks, we're referring to those sturdy blocks made from clay that have been fired to increase their strength and durability. Moving on, we see the term side air, which is a crucial concept in traditional kiln firing. Proper airflow around the bricks and clay structures ensures an even and efficient burning process, which directly impacts the quality of the final product. Now, the annular stove with pot is an interesting design. Think of it as a circular stove with a pot sitting on top. This type of stove is often used in traditional cooking setups, especially in areas where fuel efficiency is important. Speaking of fuel, it's worth emphasizing that fuel sources, whether wood, charcoal, or other biomass, are essential for firing bricks or cooking. Choosing the right fuel impacts not only the efficiency, but also the environmental footprint of the entire process. Overall, what we're seeing here is a glimpse into how simple materials like clay and innovations like specific stove designs can play a key role in traditional building and cooking methods, all of which connect back to the broader theme of sustainable, resource-efficient practices. Let's take a closer look at some key components involved in traditional stove construction. First, we have clay and bricks. These materials are essential because they provide the primary structure and insulation needed to contain heat effectively. Using durable clay and bricks ensures the stove can withstand high temperatures and last over time. Next, we see metal, which is often used for parts like the door or the flue. Metal helps improve heat transfer and durability, making the stove more efficient and easier to operate. Moving on, side air plays a crucial role in controlling the combustion process. Proper airflow, especially from the sides, ensures that the fuel burns efficiently and completely, which is vital for energy efficiency and reducing emissions. The annular stove is a specific design that incorporates these elements into a circular or ring-shaped structure. This design optimizes heat retention and distribution, making it more effective for cooking and heating. Finally, fuel is the energy source that powers the stove. The choice of fuel, whether it's wood, charcoal, or other biomass, affects the stove's performance, emissions, and overall efficiency. All of these components, clay and bricks, metal, side air, the annular stove design, and fuel, are interconnected. Together, they form the foundation for creating efficient, durable, and sustainable cooking solutions, which ties back to our overall goal of improving household energy use and reducing environmental impact. Let's take a closer look at some traditional cooking methods that have stood the test of time. Here, we see clay and bricks used to create simple but effective stoves. These are often built with side air channels, which help improve airflow and combustion efficiency. An annular stove, as shown here, features a circular design that allows for better heat distribution. It's typically used with a pot placed right on top, making it ideal for boiling or cooking foods evenly. The fuel used in these stoves usually consists of locally available materials like wood, charcoal, or agricultural waste. This setup highlights how resourcefulness and understanding of local materials can lead to practical cooking solutions. Overall, these traditional methods emphasize sustainability and accessibility, which are important themes when thinking about energy use and cooking practices in various communities. Let's take a closer look at the Bombay stove, specifically the side air and annular stove design. This type of stove is quite interesting because it features a tall structure with a chimney effect. The side air component plays a crucial role by providing the necessary airflow to ensure efficient combustion. The annular stove, characterized by its tall design, helps in creating a chimney effect that promotes better draft and improves overall fuel efficiency. This setup not only enhances heat output, but also facilitates better air circulation, which is essential for optimal performance. When we think about these designs in the context of traditional cooking methods, they highlight how engineering solutions have evolved to maximize efficiency and safety. Overall, the Bombay stove with its side air and tall annular structure exemplifies the innovative approach to stove design that balances functionality with practical use. Let's take a closer look at the Bangladesh stove design. You can see the slide shows different versions labeled Bangladesh Stove 1, 2, and 3, each representing variations in traditional cooking methods. One key feature we want to highlight is the primary air supply, which can be with or without additional air, depending on the stove design. This primary air is essential for controlling the combustion process and ensuring efficient fuel use. Next, we see the fuel feed system, which supplies the fuel to the stove, and secondary air, which is introduced to improve combustion and reduce emissions. The annular stove, shown here as tall with a chimney effect, is particularly interesting because the chimney creates a natural draft, enhancing airflow and combustion efficiency. Finally, there's a pit for ash collection, which makes cleaning easier and helps maintain the stove's performance over time. Overall, these design features are aimed at improving fuel efficiency and reducing harmful emissions, aligning with our goal of promoting cleaner, more sustainable cooking solutions in Bangladesh. Let's take a closer look at the draft air, side air, and the annular stove with chimney. These components are crucial for understanding how the system manages airflow and combustion. Draft air, of course, is essential for drawing in fresh air to support combustion, ensuring the system operates efficiently. Side air refers to the specific entry points where air enters the stove, which can influence the combustion process and overall efficiency. The annular stove with chimney plays a key role in venting out the combustion gases safely, while also helping to maintain proper draft. It's important to see how these elements work together to optimize performance and safety in the overall design. This interconnected understanding is fundamental as we move forward in discussing system efficiency and emission control. Now let's take a closer look at the good stove design, specifically the two-pot setup. When we talk about a good stove, One of the key features is the grate, which provides a stable platform for the pots and allows air to flow underneath for efficient combustion. Next, we have the draft air, which is crucial for maintaining the right airflow to keep the fire burning steadily. Proper draft air ensures that the fuel burns completely and efficiently. Then there's the primary air, which enters directly into the combustion chamber and is essential for initiating and sustaining the fire. Alongside that, side air also plays a role in improving combustion by providing additional oxygen from the sides. Moving on, the annular stove, which includes a chimney and grate, is a popular design because it effectively directs smoke and gases away from the cooking area. The chimney helps with proper ventilation, improving safety and efficiency. Finally, fuel is at the core of all these components. Selecting the right fuel type and ensuring it is properly fed into the stove is fundamental for optimal performance. All these elements, grate, draft air, primary and side air, chimney, work together to create a more efficient, cleaner, and safer cooking process. Connecting these points to our overall theme, understanding these design features helps us develop stoves that are not only effective, but also environmentally friendly and accessible to users. Let's take a closer look at the Good Stove Portable, specifically the Good Stove Single Pot model. One of the key features here is the draft air, which plays a crucial role in how efficiently the stove burns fuel. Proper airflow helps ensure complete combustion, making the stove more efficient and reducing emissions. Next, we see the grate, which supports the fuel and allows air to circulate underneath, enhancing combustion. The primary air enters from below the grate, providing the main oxygen supply for burning. There's also side air, which can help improve airflow and combustion stability, especially in different environmental conditions. Now, moving to the annular stove design, which is raised to create a chimney effect and improve airflow. Elevating the stove helps draw air through the combustion chamber naturally, increasing efficiency. The raised grate, combined with the chimney effect, optimizes fuel burning and heat transfer. Finally, all these features work together around the fuel, which is the core of the stove's operation. Efficient fuel use is essential for energy savings and reducing environmental impact. Overall, these design elements highlight how thoughtful engineering can significantly improve stove performance, making it more effective and sustainable for users. All right, let's take a closer look at some of the key components of stove design, starting with the draft air. This is the air that enters the stove to help create the necessary combustion environment. Proper draft airflow is essential for efficient burning and controlling the fire. Next, we have the grate. The grate is where the fuel, such as wood or charcoal, sits. Its design allows air to flow upward through the fuel, ensuring good combustion. The placement and design of the grate play a crucial role in how well the stove performs. Moving on to primary air, this is the main air that enters at the bottom of the stove. It's responsible for igniting the fuel and maintaining a steady burn. Controlling primary air allows us to regulate the intensity of the fire. Side air refers to the additional air entering from the sides of the stove. It helps improve air circulation around the fuel, promoting complete combustion and reducing smoke emissions. Now, when we consider a good stove, especially one designed for 2 pots, the airflow and heat distribution must be well balanced. This ensures both pots get enough heat and fuel burns efficiently. Finally, the annular stove, which is raised for chimney effect and grate, is a clever design. Raising the stove creates a chimney effect that enhances airflow and draft. The annular shape allows for better heat distribution and easier cleanup, while the raised grate improves combustion efficiency by optimizing airflow underneath the fuel. All these features work together to improve stove performance, making them more efficient, cleaner, and easier to use. Connecting these points to our overall theme, understanding how each component influences airflow and combustion helps us design better stoves that are both effective and sustainable. Let's take a closer look at this low-cost wood gas stove, which is a great example of how simple design can make a big difference. Here, you can see the draft air flow, which is essential for maintaining proper combustion. The draft air helps draw in oxygen, fueling the fire efficiently. The grate, positioned below, supports the fuel while allowing air to circulate freely around the burning material. The primary air enters from below the grate, providing the initial oxygen needed for combustion. Secondary air, on the other hand, is introduced higher up to ensure complete burning of gases and smoke, which improves efficiency and reduces emissions. This whole setup is part of a natural draft TLUD gasifier stove, where the design takes advantage of natural convection rather than needing fans or other mechanical parts. The fuel, typically wood or biomass, is fed into the chamber, and as it heats up, gases are released and burned efficiently. This type of stove is not only affordable, but also sustainable, making it an excellent choice for communities seeking reliable and eco-friendly cooking solutions. By understanding these components and their roles, we see how simple engineering can optimize fuel use and minimize environmental impact. Let's take a closer look at the key components of the natural draft TLUD gasifier stove. Starting with the grate, this is where the fuel sits and begins to burn. Proper airflow underneath is essential to ensure efficient combustion. Moving on to the draft air, this is the air that moves through the system naturally, driven by temperature differences, without the need for fans or blowers. Next, we have the primary air, which enters from below the fuel bed and supports initial combustion. Secondary air then flows in from above or sides, helping to complete the combustion process and burn off gases released from the fuel. All of these airflows work together to optimize combustion efficiency and reduce emissions. The natural draft mechanism is what makes this stove particularly interesting. It's designed to use the natural movement of air caused by temperature differences to sustain airflow, eliminating the need for external power sources. Finally, the fuel itself is a critical component. The type, moisture content, and size of the fuel directly influence how well the stove performs. Connecting this to the bigger picture, understanding these airflow paths and how they interact with the fuel helps us improve stove design for better efficiency, cleaner burning, and ultimately, more sustainable cooking solutions. Now, let's take a closer look at the different stages and components involved in the forced air TLUD gasifier stove. Starting with MOG 1, which represents the initial phase where the fuel begins to heat up and release volatile gases. Moving to MOG 3, this stage involves the combustion of those gases, which is crucial for efficient energy output. MOG 1B is a variation of the initial stage, emphasizing the importance of proper ignition. Then we have MOG 1 cyclone, which highlights the cyclone or vortex effect that helps in better gas mixing and combustion. Lastly, MOG 4 lamp stove shows a simple, effective design for small-scale cooking using the same gasification principles. Throughout this process, the grate plays a vital role in supporting the fuel, allowing air to pass through and facilitate combustion. The draft air and forced air from the fan work together to control airflow. Primary air feeds the fuel directly, while secondary air helps complete the combustion process. Proper management of these airflows ensures the stove operates efficiently, producing clean and complete combustion of the fuel. All these components and stages are interconnected, forming a system that maximizes energy extraction from biomass while minimizing emissions. This overview ties into our broader theme of sustainable and efficient cooking solutions using innovative gasifier technology. Let's take a closer look at the forced air TLUD gasifier stove design. On this slide, you can see two main configurations, A MOG 2 and B MOG open stove. Both utilize a grate and require draft air to facilitate combustion. The key difference lies in how they manage airflow. In these designs, forced air is supplied by a fan, which significantly improves the efficiency of the combustion process. This forced airflow ensures that the primary air reaches the fuel directly beneath the grate, promoting complete combustion. Secondary air, on the other hand, is introduced above the fuel bed. This secondary air helps to burn off any remaining gases and particulates, further increasing efficiency and reducing emissions. Overall, the integration of forced air, along with proper management of primary and secondary air, is essential for optimizing the performance of these gasifier stoves. It highlights the importance of airflow control in achieving cleaner, more efficient cooking solutions, an important part of our overall goal to develop sustainable biomass stove technologies. Let's take a closer look at the components involved in a downdraft gasifier stove. At the heart of it, we have the burner, which is where the combustion process begins. The fuel, typically biomass, is fed into the system, and this is done through the biomass feed. The grate plays a crucial role here, supporting the biomass as it burns. As the fuel combusts, draft air is introduced from below through the primary air inlet to ensure complete combustion. Additionally, secondary air is supplied from above or the sides to help burn off any remaining volatile gases, making the process more efficient and cleaner. The downdraft configuration means that air flows downward through the fuel bed, which helps in producing a higher quality gas with fewer impurities. This setup is quite effective in converting biomass into useful energy while minimizing emissions. Overall, understanding how these components work together is key to optimizing the performance of a downdraft gasifier stove, especially in sustainable energy applications. Let's take a closer look at the MAGH open stove, specifically the forced air TLUD gasifier stove. This design is quite efficient because it uses forced air to improve combustion. As you can see, it includes a grate where the fuel is placed, allowing air to flow through and support the fire. The draft air, which is the air drawn into the system, helps sustain combustion by maintaining a steady flow. The forced air, supplied by a fan, ensures that the combustion process is active and efficient, especially for small-scale or community cooking applications. There's also a facility for biochar, or ash removal, which is important for maintaining the stove's performance and managing waste. Additionally, secondary air is introduced to ensure complete combustion, reducing emissions and maximizing energy output. Overall, this setup highlights how integrating forced air and proper airflow management can significantly improve stove efficiency, making it a sustainable choice. This ties back to our broader theme of promoting cleaner, more efficient cooking solutions that benefit both the environment and communities. Now let's take a closer look at the MOG CM Laxmi Natural Draft TLUD Hybrid Stove. This design is quite innovative because it combines natural draft airflow with a hybrid system to optimize combustion. As you can see, the grate plays a crucial role in supporting the fuel and allowing air to circulate underneath. The natural draft mechanism relies on the heat-induced airflow to draw in air, which improves efficiency without the need for fans or other mechanical components. The primary air and facility for biochar, or ash removal, are also key features. They make it easier to manage the residual byproducts of combustion, which is important for both efficiency and environmental considerations. Additionally, secondary air is introduced to ensure complete combustion, reducing emissions and increasing fuel efficiency. Overall, this design showcases how integrating different airflow paths and management features can enhance stove performance, aligning with our goal of creating sustainable, efficient cooking solutions. Now let's take a closer look at the Avon stove, specifically its hybrid side feed design, which is versatile for all types of fuels. This setup allows for efficient feeding of biomass through a side opening, making it adaptable to various fuel sources. As you can see, the grate plays a crucial role here, supporting the combustion process and ensuring proper airflow. The draft air, introduced beneath the grate, helps control combustion, ensuring that the fuel burns efficiently. The biomass feed is supplied from the side, allowing for continuous feeding and better management of fuel types. Another key feature is the facility for biochar and ash removal, which simplifies maintenance and helps improve the overall efficiency of the stove. The secondary air is introduced above the fuel, promoting complete combustion and reducing emissions. Finally, the fuel is fed into the combustion chamber, where all these components work together to maximize efficiency, reduce emissions, and support sustainable biomass utilization. This design not only enhances performance, but also makes the stove adaptable to different fuels, aligning with our goal of versatile, clean, and efficient cooking solutions. Now, let's take a closer look at the MAGH burner series, specifically the MAGH CM-II model. This is a hybrid TLUD stove, which means it combines features of traditional top-lit updraft designs with some innovative elements to improve efficiency and usability. It's designed to burn both fuel and charcoal, giving users flexibility depending on what's available or preferred. One of the key features is the grate, which supports the fuel inside the stove. The design incorporates natural draft, so air naturally flows through the system without the need for fans or external blowers. This makes it more reliable and easier to operate in various environments. The primary air enters through a designated facility, which also allows for biochar or ash removal. This is crucial because it helps maintain the stove's efficiency and cleanliness, making it easier to manage the combustion process over time. Secondary air plays an important role as well, introducing additional oxygen to ensure complete combustion. This not only improves fuel efficiency, but also reduces emissions, aligning with our overall goal of creating cleaner, more sustainable cooking solutions. In essence, this design integrates several key elements: fuel flexibility, natural draft, and ash management, to deliver a practical, eco-friendly stove that fits well within our broader mission of sustainable energy use and low-impact cooking. Now let's take a closer look at the Twister stove, which is a natural draft TLUD gasifier stove. As you can see, it features a grate at the bottom where the fuel sits. This design allows air to naturally flow through the system without the need for fans or external power sources. The stove is designed with natural draft principles, meaning the movement of air is driven by temperature differences and pressure variations, making it very efficient and sustainable. There's a dedicated facility for biochar or ash removal, which is really important for maintaining the stove's performance and managing waste. We also see that there's primary air, which feeds directly into the fuel bed to support combustion, and secondary air, which helps complete the combustion process above the fuel. This dual-air system ensures efficient burning and reduces emissions. Overall, the Twister stove exemplifies a simple yet effective design that maximizes efficiency while minimizing external energy needs, aligning perfectly with our goal of sustainable and accessible cooking solutions. Now, let's take a closer look at the MAGH 3G grate system. This design incorporates a side air control, which allows us to regulate the air entering the combustion chamber from the side. This feature is crucial because it helps optimize the combustion process and improve efficiency. Next, you'll notice the primary air and facility for biochar or ash removal. The primary air is essential for sustaining the combustion, while having a dedicated system for removing biochar and ash ensures the stove stays clean and maintains consistent performance over time. Moving on, there's also secondary air, which plays a vital role by providing additional oxygen to ensure complete combustion. This not only boosts efficiency, but also reduces emissions, making the stove more environmentally friendly. This system is part of a hybrid stove design, combining TLUD, which stands for top-lit updraft, and other types of fuels. This flexibility allows for the use of various biomass sources, making it adaptable to different contexts and needs. And finally, the fuel is a key aspect, whether it's wood, crop residues, or other biomass. The design's versatility ensures it can handle different fuel types efficiently, supporting sustainable cooking solutions across diverse settings. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at how the airflow works in this type of stove. The key elements here are the air feed, the pot, and the up or down draft stove. The gases produced during combustion naturally flow either up or down depending on the draft, which is driven by temperature differences and the design of the stove. Importantly, only a minimum amount of gases escape, because most of the gases are directed into the combustion chamber to sustain the fire efficiently. Now, at the base of the stove, we have the ground level and a raised platform that supports the stove itself. This setup helps improve airflow and makes maintenance easier. The channel for draft is a crucial component. It guides the gases and air flow properly, ensuring the combustion process remains steady and efficient. In the context of a Satara sugarcane juice boiling stove, this design maximizes heat transfer and minimizes fuel wastage. By managing the draft effectively, we can control the combustion process better, which is essential for consistent boiling and energy efficiency. Overall, understanding these airflow dynamics helps us optimize stove performance and improve productivity.